good afternoon. As you already anticipated, I'm going to talk about a line of research that we cultivated in the last years, dealing with the human mobility, and in particular studying how different routing policies can, let's say, affect not only efficiency of movement, so how fast a trip can be to go from A to B, but also its impact on health in general. Actually, here I will focus on emissions in, let's say, study how mobility data can be used to estimate these emissions. We will turn a little bit the head towards a more precise notion called the exposure, I will mention later, and finally discuss the core topic, which is studying routing, but for thinking to pedestrians and what is the impact of emissions on the pedestrians. Okay. The starting point is the fact that mobility, in particular vehicular mobility, so people moving using vehicles, is generating a very significant part of emissions in a urban context. Okay, so we are talking of double-digit percentages of CO2 emissions in the city come from vehicles moving around. Of course, that has a strong impact on the environment in general, but, and that's the focus of my presentation, also a direct impact on the health of citizens. Okay, we simply breathe these emissions. Okay. The line of research I want to describe you started a few years ago, trying to, let's say, study what is the, let's say, the contribution of vehicular mobility to CO2 emissions from a big data perspective. Okay, that's our background. Okay. So we have data of moving vehicles, like GPS traces of cars in the city. We studied a way to translate this into estimates of CO2 produced by these vehicles. Okay, that basically consisted in, let's say, applying some well-known mathematical model that says, okay, if the vehicle is of this type, and so the engine of this type, and the vehicle moved with this speed and acceleration in this area, then the instantaneous production of CO2 will be this amount. Okay, it is an extremely simple formula with a lot of parameters, and the trick is to, let's say, fit these parameters, but somebody else did the work, and so we simply inherited it. Just fitting it to the specific kind of vehicles we had. And so we can turn simple GPS traces, points in space, into emission points. Okay, so we can, let's say, in some sense, spread the CO2 emissions generated by vehicles on the map. And with this study, how much each vehicle is producing, for instance, or when, and obviously where. And that's where, that's how we can produce, let's say, nice-looking maps like this, even though the hidden message is not nice-looking at all, because those are emissions. So, okay, but this is London. Don't worry. For Italian cities, much better. No, it is much more. I live in London. You live in London. Yeah. Okay. I'm not showing the other one we have, which is Rome, which is much worse. So just to show you out. Okay. This allows us to study also how these emissions are distributed on the map. That depending on the city, let's say, follows different patterns. But what you get in general is that you have areas with a higher concentration against areas with a much lower concentration. Of course, we expected that, but in some cities is particularly clear, and the difference between the two parts can be very, very strong. Okay. As I say, our work, the part that I'm going to present today, actually comes from a shift of focus. So instead of talking about emissions we care more about the exposure of humans to these emissions. So, as I said, what you breathe, living or moving in the city every day. The idea is basically that, of course, talking in general about the environment, the more emissions you have, the worse it is, right? We all agree about that. But in terms of, let's say, safety of the common citizen that is walking around in the city, it makes a big difference whether these emissions, like here in the top right, are produced a bit far from the ground, or instead is very near the ground. So it could happen that some higher emission level areas, like the top right, which are bad in terms of emissions, are actually not so dramatic in terms of direct impact on the individual, so in terms of exposure of humans. And on the contrary, other areas which look at milder in terms of emission production actually might host the citizens moving or staying there, and therefore those lower emission levels actually have a higher impact on population than the let's say the other the higher emission level areas. So we focus on exposure on humans. Sorry, this thing is counterintuitive. As you have learned today, it's not intuitive. So we take as a representative case the viewpoint of pedestrians, but 99% of what I'm saying applies also to bicycles or, I mean, anything humans can move on without an engine, more or less. And the point is that walking means moving from A to B, but if we think about emissions, also exposing ourselves to those emissions. So when we evaluate how good is a trip for reaching a destination, we should not only think about how fast it is, but also how much exposure I get from that trip. Here on the right, you see an example where we have 4 trips generated by Google Maps, okay, for going from a common origin to a common destination, from the Polo Fibonacci in Pisa to the train station, more specifically, for those that are familiar with the area. And we use these 4 routes suggested, evaluating travel time and the exposure based on the emission levels that we obtain from, let's say, the vehicular data. Okay. What you obtain is that there are indeed some differences in terms of exposure and time. In some cases, these differences can be very large. For instance, the yellow route, which follows, let's say, rather traffic dense areas of Pisa. I mean, this is the roundabout of death, let's say. If you are a commuter to Pisa, you know that you can spend let's say, unlimited amounts of time, so produce emissions in industrial levels. And you see here that the exposure is 1.21, whereas the let's say the simpler way for a pedestrian, which crosses mostly pedestrian-only areas, and so they are relatively far from the traffic. The exposure is like 1/3. Okay, so that can be a huge difference. In this example, instead, the time difference is quite marginal in some sense. Okay, it's like 10%, 5%, 15% at most. Okay. So we, in general, we want to consider 2 objectives when we plan a trip for pedestrians, which is efficiency, shortest trip, but and the second is exposure. So we want to minimize exposure as much as possible. For some reason, the trip suggested by Google Maps seems to be coherent. The more you walk, the more you get exposed, but that does not happen in general. I mean, empirically, we found that that is not that, and usually they conflict. Okay, the most efficient say route which does not consider health issues is efficient, but usually you get more exposure. But there are other, let's say, the routing that are better in terms of emissions. We implemented this idea in a very simple way. We defined the cost of a trip as a simple linear combination, convex combination of time cost and the exposure cost. Exposure can be computed very easily by assuming some parameters like breath rate, etc., the weight of the person, the speed of walking. Just take a reasonable fixed parameter values, and that becomes easy to estimate.
Exposure is a maximum value of this quantity exposure, the parameter exposure.
Exposure is
where it varies from 0 to.
Oh, it's unlimited. It depends on how many.
What means in
Yeah, I mean, this is basically the expected amount of emissions, so milligrams of CO2 in this case, that a person walking on that road on that path is absorbing. So there is not a predefined bound, of course. Above a limit, you die while walking, so it's not infinite, but I cannot tell you what is there.
Let me explain the problem. As a physicist, you're using time and exposure, so they appear not to be commensurate.
I try to trick you to save time in presentation. So W is not only the importance that I give to one parameter or the other, but it's also a conversion can be. But actually, there is a second trick that I really didn't want to explain, but the fact that when we compute this cost, we use normalized time and normalized. So everything becomes between 0 and 1, basically, and so it's easier to reason. So W indeed is kind of the importance, 20% against 80%, for instance. Okay. So the idea is that changing this value, this mixture of cost gives more importance to one or the other parameter, and you can see an example here. If I set W very high, basically I care about time. You could get a trip like the green here, you see, that goes straight from the origin to the destination. If I get I fix W to a very small value, 0.01, I care mostly about the health. You see that the corresponding trip is much longer, but it avoids these red stains, which are the most, let's say, polluted ones. Okay. Again, this heat map you see below is the emissions derived from mobility data with the model I explained to you. Okay, so the point here is how to choose this W first, and second, should this W be the same for everybody, for every trip, or should be adapted in some way? This is a very strong practical consequences, of course. Why? Because in most papers in the literature, the authors in some at page, I don't know, 10, in the middle of the paper, decide a good value for W is 0.83, for instance. And that's it. Nobody discusses the topic anymore. But if you want to make a choice which is individual, in theory, you should fix a W for each trip. And if you have 1 million trips, that takes a bit too much time. So we need a more systematic way to do that. And we applied a very simple idea. We said, okay, let's compute the results for several different values of W. We get a Pareto front, where we have on one extreme faster routes, but that expose you more. And on the other extreme, the opposite. Slower, but with less exposure. What we want to do is to find the best trade-off here, and we applied a simple heuristic. This is called maximum hypervalue, but just compute a kind of area covered, dominated by each of these points. In this case, if we decide that the choice must be collective, the optimum we get is the red point here. If you apply an individual one, you get the green point here, which is slightly different. Okay. What you get in this example, for instance, which is from a real simulation, is that we have a 15% reduction in exposure, so quite significant, at a cost of less than 5% increase in travel time. The next step, and the last one, since I have like 3 minutes left, is to consider the fact that even vehicles could collaborate in minimizing the impact in exposure, which means it's not that we have like this a fixed map of emissions caused by vehicles and nobody can question about the trips of the vehicles, but also the trips of the vehicles can be, let's say, put into discussion. Okay, we have then a complex interaction between pedestrians and vehicles, and to summarize it briefly, what happens is basically that when vehicles decide the routes to follow, basically they decide what is the potential exposure of the different portions of the map. Then, when pedestrians decide where to walk, basically, they are, let's say, absorbing the emissions generated by the corresponding trips of the vehicles. What you get is a kind of product of two maps. Here, where pedestrians go, with here, where the vehicles go. And what you obtain is this final result, which is the actual exposure. I mean, how much CO2 was absorbed by humans in the different roads of the map. And you see that there are some areas where the exposure is much higher than others. It's the actual exposure, say, exposure in action in some sense. Because there are areas where there are more vehicles, they pollute more there because maybe they go faster, and a lot of people go there walking. So what we did was to implement a very simple optimization schema, a two-step optimization. In one, we fix the route of the pedestrians. We decide they walk like this today, and see how we can reroute vehicles in order to reduce the impact on the health of these pedestrians, while not disrupting completely the efficiency of the trip, of course. After that, we fix the vehicle routes and instead optimize the pedestrian route, like we did in the previous. So we get this kind of evolution, okay? We have an initial distribution of vehicles, the initial distribution of pedestrians, then the vehicles adapt a little bit, but then the pedestrians adapt a little bit to the most recent vehicle routes, and so on till we reach a convergence. Some results, just very, very quickly. This process has a clear effect. This is what happens if vehicles and pedestrians do not talk with each other, basically. And what you see on the right part is what happens if they collaborate in the way I described. You see that there are very few spots with, let's say, high exposure. We removed most of them in the city center. Something in this area is remained, but it's irreducible, apparently. In particular, if we plot for each road segment, let's say how many pedestrians passed there and how much emission was produced there, we see that from the initial distribution, where we have this danger zone, a lot of people go where there is a lot of emission. This danger zone is almost empty. Okay, so people either went in different parts, walked in different parts, or vehicles were routed in different places. Okay. And finally, we have some numbers, but let me go to the conclusion where I summarize these numbers. Basically, we can have a significant improvement in human exposure with moderate to negligible impact on other quantities like efficiency of the trips. What is next? Well, first of all, understand what happens on large or very large cities, where things get more complex, not only larger, but the, let's say, interference between the two walls can be more difficult to model. And how much can we improve the optimization of risk that I mentioned, which is very basic, very efficient, but also very naive in some sense. Many others, but of course my time is over. Thank you, and I'm happy if you have questions and time to answer.
Thank you, Mirco. Alice, we have time for one question, if any. Please.
So it has been my experience that Google Maps is quite optimistic about walking time because it doesn't really factor in average walking speed. I think it factors in 6-foot-tall man with long legs that goes like a New York City pedestrian. And so when you calculate your exposure risk, you take into the fact that there's no way that every routing is going to be accurate as far as speed goes.
Yeah, let's say.
Because it should increase exposure if you're walking slower. Yeah.
That is true. We adopt a very simple, let's say, a very strong simplification where we assume a fixed speed. I know that there are athletes that walk like as fast as I run, let's say, and vice versa. But let's say we took kind of the average case into consideration in middle, the average adult that is no specific, it's not hurrying, but it's not a tourist, let's say. So we have a fixed speed taken from the literature. On the other, the vehicles instead here simply travel at the speed limit. And also that we know it's a strong simplification. In some cases you cannot drive that faster. In some cases you cannot drive that slow because we are in Italy and etc. And speed limits are suggestions in some cases, or are written as suggestions. And by the way, this opens also another chapter that I want not to touch too much, but even modulating the speed for the vehicle can modulate the emissions. And so maybe in some cases you could go a bit slower and get a better trade-off. You spend like 5 seconds more, but maybe it's a highly populated areas, and so the impact, the benefit in terms of exposure is 50%.
So that would be a policy thing.
The first one is more cultural.
Yes,
I don't
the
respect
second-
speed limits.
right.
There are already the policies there, but
Yeah.
the second one is, could be something kind of suggestion that a smart vehicle can give to the driver.
Okay, let's thank Mirco again.